Rob Fon to introduce Emily.
I'm Rob Pond, Chair of Engineering, and introduce you to Emily Mansour. And Emily's a rising junior in our program, and she's concentrating in both mechanical engineering and materials engineering. She came to me last winter, and I knew she was a RA and on the Honors Council doing an internship and a Division I athlete. And so she was looking for something to do with her spare time and asked if she could do a research project. So I listed for her 4 or 5 items that she could possibly do. And the one she chose is one that was of personal interest to me because I'm in an intense program of domestication called marriage. And in that program, I have to wash dishes, and this will become clear when she gives her talk. So we engaged for 1 semester and made application for Hauber, and she will reflect on the work she's done so far on the blacksmith's paradox. Emily.
Thank you so much, Dr. Pond, for the introduction. Only nice things were said. That's good. As he mentioned, I am Emily Mansour, and my project is the blacksmith's paradox. Okay. As far as the history that he was talking about in the background, the blacksmith's paradox obviously originated with blacksmithing, which is where they would take long bars of steel, cast iron, and actually heat them in a forge during their everyday job. Typically, then they would quench these bars quickly in a vat of water to cool them down. Obviously, me and Dr. Pond are not blacksmithing on a day-to-day basis, but we are both cooking. So a similar process is actually seen in cast iron cookware. So this is when you're washing the cast iron pan, you don't want to put it away wet because you'll actually ruin your pan. So you actually put it on the stove, reheat it, and then to store it, you would quench it again. And when you're doing this, you actually observe a rapid rise in temperature of the handle, which most people will actually drop the pan. So this is what he mentioned in his introduction. And as far as the apparent conditions that are required with this is we are seeing that it needs to be a steel ferrous alloy. The bar has to be heated at one end, and there also has to be a rapid quenching of that same heat end. As far as a literature search, we did look into this fully to see if there was an explanation for this that had already been published, and really to see if this was a significant research topic that we wanted to dive into more. So we found one article that was on the topic called Thermal Conduction and the Blacksmith's Paradox. It was actually published in 1981. And this is a kind of reverse experiment, is how they describe it to the blacksmith's paradox. They actually submerged a round-nosed steel object into molten aluminum. Then they measured the homologous cooling in the interior of the steel. So again, this is a reverse experiment to what me and Dr. Pond are doing. Then they explain the effect of thermal expansion of the exterior, creating a transient adiabatic expansion and cooling of the interior. This is actually a quote from the paper they did publish in the European Journal of Physics. And the first paragraph is very significant because, as they state that their experiment is not really relevant to the blacksmith's paradox at all. However, they do go on to give a reason for the blacksmith's paradox, even though they just said their experiment wasn't relevant. So the last 2 paragraphs are also very important because there's a lot of conjecture about this effect being a biological or psychological effect. I know some people in the room hold that belief too. So this is kind of what they came up with for their conclusion. As far as our research idea, so the main beginning of our research was to replicate what we were experiencing with frying pans and what blacksmiths were experiencing in their day-to-day lives. So we wanted to heat and quench the bar, different metals, as was seen throughout history. And then we wanted to make measurements of the temperature in the quenched metallic bars as a function of time. So we'd be using the infrared technology to actually do this very definitively. And then thirdly, we wanted to make a computer model of the transient behavior and compare that model to the experimental results we were getting, so we would have something to base our results off of. As far as IR measurements, so we actually have this camera here at Loyola, and this is actually a picture of me. I was trying to study for an exam while Dr. Khan was playing with his new toy. And we can actually use this to go into this image and pinpoint any pixel, and it'll give us an accurate temperature reading of that point. Obviously, we need to look at classical modeling, which is a little difficult for me because I had not gone through these classes yet as just a rising junior. So I really leaned on Dr. Bailey for this part, as far as SolidWorks, to go through the modeling software and develop accurate models that we can actually use for our analysis. So with the SolidWorks modeling software, we actually could put in the thermal, material, geometric, and boundary conditions that would predict the thermal transients at times and positions. So we're still working on that right now to change the variables here and there to get the most accurate model compared to our experimental setup. And as you can see on the bottom, this is just a typical temperature gradient of the steel bar that we'd be heating. In terms of classical theory, when you're quenching a bar, there's obviously going to be heat transfer into the water coming off the one end, and there's going to be heat transfer along the bar in the other end. And then the temperature will continue to rise in the rest of the bar on the other end when you are quenching in terms of classical theory. But the interesting thing for our research, at least, is this last bullet point, which is by how much and in what time frame. So we're actually aiming to say that we're seeing a greater rise in temperature than classical modeling, and we're seeing it in a faster time frame than the classical model. So as far as SolidWorks modeling, we wanted to create a model with relevant specific variables that would actually demonstrate the heated and quenched bar. So this is actually a model that Dr. Bailey gratefully made for us, and you can see the 0-second plot, the darker green line here, is the initial thermal plot of the bar, and then the lighter green is actually after the quench condition. So you'll see that the heat does transfer to the rest of the bar, which is going towards the left, and to the right, which is into the water now. And then this is actually a blow-up of the same image, which kind of highlights what we're looking at here. And as you'll see, there's a max delta T of about 3 degrees with this, so that's what we took to be our first model of expected temperature rise with our conditions. So initial experiments, this is when we started experimenting at Loyola. We actually started with round test subjects of gray cast iron, which didn't really work out. There's a lot of things that we had to go through and change and tweak here and there. And this was the first one of our hiccups. But we were finding that there were problems with the curved surfaces viewing through the IR camera, so we couldn't get an accurate measurement of the temperature at certain points. So then we moved on to square cross-section, still remaining with the gray cast iron bars. We also saw a little bit of a problem in this. So when we were looking at the images, the graphs weren't very smooth. They were a little bumpy in terms of emissivity. So we actually, Dr. Kranoff helped us here to machine the bars to make them extremely smooth, and then we actually painted them flat black for emissivity purposes to make sure that was uniform throughout to help with our measurements. So this image here is actually 4 bars lying next to each other with the flat black, and you can see the original metal on the top there. This is what our test subjects actually look like. And then you'll see there's a band of the metal going across right next to the flat black, which is actually where we're using to take our measurements off of to measure different spot temperatures throughout the world. And then the last issue we had here was the frame capture rate of the camera is about 6 to 7 seconds for one image for the camera I showed you before, and we're experiencing this in about 1 to 3 seconds. So that was a huge problem for us. So we really had to try to work through that and see where we could go, find another camera. So this is actually the experimental setup. Everything is labeled there with what that is. The one huge thing to note here is the steel barrier. We were having a lot of problems with steam and water particles actually coming from the quench to interrupt the left-hand side of that barrier. That was actually causing issues with our results. So we created that barrier so we can stop that as much as we could. Next, we have our initial experimental results actually taken at Loyola. And in this, we find that the max delta T is approximately 15 degrees Fahrenheit. And this is a gray cast iron specimen that has been quenched. So you'll see on this graph, the x-axis is actually points along the bar. So we go in with the IR and we pick different uniform pixels throughout the bar, and then we'll actually plot the temperatures at those points to get a gradient throughout the bar. So the green dot is before the quenching, and most notably the red dot, the 2 seconds, is after the quenching. So that is where we're seeing about a 15-degree rise in temperature for that. So next, to try to avoid our camera issues, we actually paired with Dr. Hiley, who's an Loyola affiliate faculty. He actually teaches in the engineering department, but he works at Aberdeen Proving Ground full-time. So that offered us a more advanced IR technology. Their camera's about $250,000, about 4 times the size of ours, and was really beneficial to our research. So it has a maximum frame rate of hundreds of hertz. So we can actually go up to, I think it's 600 hertz per second max, which is way better than our cameras. We're actually able to find data more accurately. This also had a better plotting system, so the software we were using was way more advanced. So we were able to look at different types of data analysis for that. And then we went into testing other types of materials. As I said before, primarily all of our data was captured around gray cast iron, because that's experimentally like what we had seen. But so we went into copper, aluminum alloy, brass, steel, and cast iron. In terms of preliminary results, gray cast iron has a measurable temperature rise above the predicted. And again, the predicted was at 3 degrees from Dr. Bailey's modeling. And then I showed you the 15-degree rise in temperature, which is what this point is talking about. And then the Aberdeen Proving Ground test data is still being analyzed. This is actually a graph that is outputted from their software. But the main thing we can see here is that to see the same rise in temperature between a quenched and non-quenched cast iron bar, it's taking about a third of the time less for the same temperature rise to happen in a quenched bar versus a non-quenched bar. In terms of future work, at Aberdeen Proving Ground, we're working to use surface thermocouples, which will give us another measure of temperature versus time, which will back us up with our IR data to have 2 methods of conclusion for that. We're also moving into oxyacetylene heating, which will allow us for steeper temperature gradients, as I mentioned before. It's very important to have steep temperature gradients for the phenomenon to actually occur. And then lastly, in terms of looking into geometry. So we actually have flat bars in the metals that I mentioned before that are going to be machined into a funnel shape, which will allow for a greater volume to be heated to see if the effect increases with the increased volume. This is actually an image of what those will look like when they are completed. They're about a foot long, and as you'll note here, they can be used at either end. So the right-hand side here is what we've been doing, the square cross-section, heating that up. So we can look at that, gather data from that, cool it down, and then actually flip it over and look at the results from the higher volume funnel shape as well. In terms of theory, we're thinking electrons, phonons. There's a lot of different theories, especially for all the physicists in the room. But I think first things first, we need to determine if it's real or not before we can go into conjecture of the theory. And there's a lot more data that needs to be gathered. I've been working on this project for over a year now, and we're still not completed with it. So there's a lot of data that needs to be gathered. It's a day-to-day process getting there, but we need to decide if it's real first. And then in terms of applications, I know especially up at the Army, everyone's asking me, well, what are you going to do with it? How is this going to be useful? And again, similar to the last slide, we first need to determine if it's real before we can say we can use it for this, we can use it for that. So that's really important to us, is having a definitive answer to say, yes, this is real, no, this is not, and then proving either way once we have that baseline data. And lastly, I would like to thank the following individuals. Dr. Bailey has helped me with the SolidWorks. Dr. Hiley up at Aberdeen Proving Ground, who's also at Loyola. He's been my internship mentor there. Dr. Krenos in the machine shop, everything I need. He's been extremely helpful. And of course, Dr. Pond, who you can see below. This time I was playing around with the camera. He's been greatly helpful to me, working with me up at Aberdeen as well. So, thank you very much.
Questions?
My question has to do with the surfaces of your materials. So number one, when you use the IR camera, are you just measuring the temperature of the surface of the material? And then number two, when you do computational modeling, are you considering the temperature of the surface? So your experiment is at room temperature. But in your picture, it looked like it was a 1D model. So I'm just confused by the temperatures you're measuring.
So we're measuring the temperatures off one face of the bar. And then we're measuring the surface temperatures with the camera, because that is what the camera does. We did move into ladder bars. The bars we're using for most of this data are about 1 inch by 1 inch. So we started moving into 1 inch by 1/8 of an inch to try to avoid any interior data that we would be missing from the camera when we're doing the surface temperatures. Did I answer your? There's a lot of parts there.
Yeah, exactly. There are a lot of issues with this problem, so some of it is not enough time to explore it.
Yeah, since you asked for feedback from the physics community in a sense, I mean, I presume you know that the physics community pretty much feels this phenomenon doesn't exist and it's a psychological phenomenon. But this is like a perfect example of kind of the way science works, because nothing's ever like a done deal, right? In the science realm, even if you have the entire physics community convinced that this stuff doesn't really exist, it always makes sense to be sort of having people out there doing the experiments to see, because once in a while you do discover something quite surprising. This would actually be quite surprising, because it's unlikely that phonons or electrons could sort of explain that. So when you give your presentation next, you might want to be a little more upfront to say, this maybe doesn't exist, but if it did, it would actually be very revolutionary. So in a sense, you are really sort of looking for some very sort of surprising results. That being the case, also it takes very firm evidence before, when you're trying to sort of show that something exists that most of the community feels doesn't. It takes a lot of good solid evidence. So yes, if you've been working on it for a year, it's a start.
Yeah. There's 2 more here, so we'll see where it goes. Anyone?
You did mention on the sensory end that it might be vibration. I think that's, would there be any way that you could start to measure that to see if that is occurring?
So we haven't, I've obviously read that paper countless amount of times, but we haven't really taken their conclusions to be even close to realistic at all. I know occasionally we kind of look at it like, where did they get that from? That's absurd. Because they don't really have any data to support that. They kind of do this whole experiment based on something So we haven't looked into that whatsoever. We're trying to examine, what we think it possibly could be first. And then I'm sure if we hit a dead end there, then we'll go into possible, we'll look at that paper, we'll look at other people's theories and see if there's something to try next. But as for right now, we haven't looked into it at all.
We'll keep talking. Maybe looking for another experiment. Fanny Farmer cookbook from 100 years ago had talked about when you cook eggs, that if you take them out of the boiling water and you plunge them into cold water, that drives the heat into the center and it will help cook the second egg. And again, that's something that pretty much people think is total nonsense, but there's another experiment. It might even be simpler to see if there's some truth to that, if not in the current version.
Any other questions? No? All right.